This conference will now be recorded.
Very good evening, students. So we have been discussing about ray optics, and we have already discussed what are spherical mirrors and what are the basic laws of reflection, which are valid for plane mirrors as well as the curved mirrors. And also we have seen how the images are formed in convex and concave mirror. In concave mirror, we have seen that the image can be of two types. One is real most of the time. So real images which are cast on the screen, and if we keep the object between pole and focus, then virtual image, virtual and erect image. So virtual and erect image is formed, and obviously magnified image. So today we'll see those things. Actually we had analytically we have seen, just if you have been given a position, like if the object is being kept at the 2C, sorry, at the 2F or at the C, center of curvature, where the image will form, the nature of the images we can so far say about these informations just by drawing. Okay, just by drawing. But analytically, without drawing the figure itself or the geometric formation, image formation, without doing that, also you can say the position, you can say the nature of the image and things like that. So you can just by doing a small calculation from, okay, so you can just do a small calculation and you can say those things. But how to do that calculation or where to get that informations, to know that, actually we'll learn today the mirror equation. I had already told you a little bit about it. So see the position, if this is the position of the object, suppose AB is an object. So the distance of the object from the pole is called object distance, which is denoted by U. You can see that. Okay, and suppose the B prime and A prime is the image formed by this concave mirror, and this is the image. A prime B prime is the image of this AB object, and see the position is B prime P. This position is denoted by, this distance is denoted by V. So image distance, so object distance is denoted by object distance, and all the distances are measured from the pole. Okay, object distance is U. According to sign convention, I'll tell you, according to sign convention it is minus U, and image distance is denoted by minus V in this case. Actually V, but with sign is minus V, and focal length is in this case minus F. All three are minus quantities because we are measuring these distances from the pole to leftwards, okay, or along the negative x-axis. In terms of our discussions, previous discussions, we had considered pole as the origin, and we had drawn y-axis in the upward direction, okay, and x-axis we had taken in this direction, okay. Then in this side is negative x-axis, etc. So here we have a particular equation with these three, like with which these three are related. Okay, these three, image distance, focal length, and object distance, they are related by a particular equation that is called mirror equation, that is 1 by u plus 1 by v is equal to 1 by f. This is called mirror equation. And see, today's task is to find out this, derive this equation. Okay, we will derive only for the concave mirror, and this equation is same for both the concave and convex mirror. So we'll just derive this equation, 1 by v plus 1 by u is equal to 1 by f, or 1 by u plus 1 by v is equal to 1 by f. Okay, this is called mirror equation. So somewhat I had given you the introduction about this equation and why do we need this. Actually, analytical calculation we can do, or just by doing a little bit of calculation we can easily say the position, what we can say, position of the image, or if the position of the image is given, then we can obtain the position of the object. Okay, position of object, image, okay, and nature of the image. So these informations we can obtain. Okay, nature of the image. Okay, so these are the informations we can obtain from this particular equation, mirror equation. We'll obviously take up numerical examples or numerical problems after deriving this equation today. Okay, so let us just go for the derivation, and I'll erase these things. Let me first once again, let me first tell you about this figure. So this, as you know, this is actually polished surface. This is a concave mirror. Okay, so this is mirror equation for concave mirror. We are going to do concave mirror. Okay, so this is the concave mirror. N, this is the mirror you said, and P is the pole. Okay, so the curvature, see this aperture is such that this MP has to be taken as a perpendicular line on the principal axis. Okay, so curvature is like, if it is having a small aperture, it could have been like this. Oh, sorry. So it would have been a straight line. This MP would have been a straight line or perpendicular to principal axis. That is what I am trying to say. And see, since BP and AM, these are parallel lines, so AB can be equivalently written as MP. So these considerations we will take. By mistake, I had just erased this also. So these considerations will take. Say I'll write one thing more here. So this is perpendicular to BP. I will write perpendicular to BP for small aperture approximation. Okay. So here, as you see, as I was discussing, that there is an object AB in front of this concave spherical mirror, and say I'll just try to find out geometrically or just by doing the arrow diagram. If we just take three rays, like one parallel ray, according to the rules of image formation, if we take a parallel ray, see, if we take the ray from point A, which is parallel to the principal axis, after reflection on the mirror, it will just pass through the focus, right? It will pass through the principal focus, or yeah, so that's point. Then if I take a ray which is passing through the center of curvature, you know, this center of curvature, a line from center of curvature to the mirror will be perpendicular to the mirror. So there is, say, in case of plane mirror, normal incidence. Okay, If the ray is coming like this, it will just retrace the path. So that is happening here also. So it is retracing. You can see this is the reflected ray. Now I can take another ray which is an oblique ray. Oblique ray in the sense it is making certain angle. Okay, certain angle at the mirror. So if this is the angle of incidence, then this will be angle of reflection according to the law of reflection. It should be equal. Okay, angle I should be equal to angle R. Okay, so if we just follow these rules, we can get the image of that object. As you see here, we are getting the object. I'm just not messing the figure because it is crucial. So the image, so I'll write here, object is AB, and image of AB is B prime A prime or A prime B prime, whatever you say. I'm saying B prime A prime, and it is actually inverted. You can see that inverted image. So it is real image obviously, but we are not going to that point. See here, so this is image, right? So A prime, see A prime is image of A. Okay, similarly B prime is image of B. If we take any point in between, so from there also light rays will get reflected, and you eventually will get those lights emitting somewhere here, like that. Okay, so that's how we get the image. Okay, so far it is fine. So keeping these points here in the left hand side, I'll keep. So AB could be written as MP. Again, MP is perpendicular to BP. So these points I'm just considering. Okay, now I'll just write on the right hand side. Let me just tell you this. See, I'll be purely using geometrical considerations. So that's why this ray optics is also known as geometrical optics. So here, you look, I'll just take two triangles. What are those? There are two right angle triangles I'll consider. So the triangle B prime A prime F and M F P. These are two triangles. Okay, look, these triangles are actually similar triangle. Okay, similar triangles. Okay, because see, this angle is 90 degree. In this case, this angle is 90 degree, and this angle, these two angles are actually common to each other. So if there are two angles equal, then we may say that these triangles are similar triangle. So similar triangle we can write from this, since these are similar triangles, I'll write these are similar triangles. Okay, similar triangles. If these are similar triangles, then I can write, see, B prime A prime, B prime A prime divided by this MP. I can write, isn't it? I can write that, and I can write this is B prime F. Okay, this is equal to AP. This I can write. See, since MP, see, since this AM ray is parallel to AP, we can write MP is equal to AB also. So I can write this as B prime A prime divided by AB. This I can write, isn't it? B prime F and FP. Now look, this is suppose this is equation number 1. Now look, I'll take two more triangles. See, I'll take triangle APB, and the same triangle. No, not the same triangle. I'm just going to take A prime P B prime. These triangles. Okay. So from this triangle, see, we can see this for this triangle, the angle P, this particular angle APB and this APB prime. These are actually equal angle, isn't it? I'll tell you why. See, APB. This is angle of incidence, I say, and this will be equal to angle of reflection, that is actually A prime P B prime. Okay, I hope you agree with me. See, this angle is 90 degree again, and here this is 90 degree, right? So these two are also similar triangle. Okay, similar triangle. These are also similar triangles, right? These two are also similar triangles. Then see, from the similar triangle consideration, so if these two are similar triangle, then what I'll write, see, from this we can write A B prime A prime, let us see, B prime A prime divided by BA or AB, same thing. B prime A prime, we can write AB or BA, both are same actually. Okay, this I could write this as BA. This is equal to, see, I can write APB, right? So I can write B prime P divided by B prime P means this one, so this will be divided by BP. Okay, divided by BP. Look here, if I compare these two, equation number 1 and equation number 2. Comparing equation number 1 and 2, because the left hand side, see, these two quantities are same. I can compare and write. So comparing equation 1 and 2, equations 1 and 2, I can write B prime F divided by FP, B prime F divided by FP is equal to B prime P by BP. B prime P by BP. Look, I think I record this figure here to make you understand the length properly. So I'll keep this figure here somewhere. Let us just keep this figure here. Okay. So B prime F, that means this particular length, B prime F. Okay. So this length, let us see if we can write this way. I'm sorry, this is just blinking. It will take 1 or 2 minutes. Okay, I hope, yeah, now it has gone. Now see, B prime if I can write in this way, look, B prime if, right? Look, if I can write this way, B prime P minus AP divided by AP. This is B prime P by BP. This is B prime P as it is. I'm keeping BP. Now look these distances. What is B prime P? B prime P, look this B prime P, this is actually the image distance. So I can write with the proper sign. B prime P, I'm measuring the distance from pole to this B prime. So I'll take this as minus V because this is image distance V. Look, this is the one denoted here. Now what is FP? This FP is nothing but the focal length, and that is also with a negative sign. What else is remaining? BP. This BP, this is the object distance you see, this is U with a minus sign U. Okay, now see, if I just put all these values, B prime P, I'll put here as minus V. FP, I'll write minus F. Okay, with the minus sign, so this will be positive. Now divided by FP with the minus sign F. Right hand side, this is B prime P, this is again minus F. I'm sorry, this is minus B divided by BP. BP is minus U. Okay. Now see, we have to, okay, so if we just divide this V by F, this will be with the minus sign 1, and this side minus V by U as it is. Okay. Look, now what we'll do, we'll just divide with V. Okay, this is suppose equation number 3. I'm dividing this equation with minus V. Dividing equation 3 by minus B. Look here what we are going to get. See, minus B means this will strike out with plus sign, so it will be 1 by F. 1 by F. There was minus 1 here. I'm dividing with minus B, so it will be plus 1 by B. 1 by B. And you look this right hand side, I'll get minus 1 by U. Minus 1 by U. Minus 1 by U. I think there is some mistake over here. I'll just check. Okay, so this will be plus. Okay, this will be plus. This is the mistake I had done here. So this will be minus after dividing. Okay, so look here. I'll just keep this. See, I'll just transfer this to left hand side. So I'll get 1 by P plus 1 by U is equal to 1 by F. If I just take this on right hand side, just rearranging. So this is actually mirror equation. Mirror equation. Okay, this is mirror equation. All right. So this is the way we have to derive the mirror equation. Okay. So you look, this is the particular figure I have used. This is a concave mirror. In case of concave mirror, we have derived now. You can just do the similar geometrical consideration, and you can derive the equation, mirror equation for convex mirror also. So this is actually called mirror equation. So this mirror equation is sometimes called mirror formula also. Mirror formula also. See, as we progress in this chapter, we will learn similar kind of formula for lens also while studying spherical lenses. So in that case, you know, that will be u 1 by v minus 1 by u is equal to 1 by f. This is actually lens makers formula. Okay, so that will or lens formula. This is formula for the lens. Okay, you should not confuse yourself. So this is mirror equation. Now we'll learn another term called, see here, you know, this. So this, the beauty of this equation is, see, there are three parameters, u, v, and f. If one among them is missing and others are known, then you can find out easily the third parameter. Okay, if one among these parameters is unknown but the two of them are known, then you can find out the unknown parameter using this equation. I'm doing very simple calculation, but in this case you need to know that you have to take the u, v, and f with proper sign. With proper sign while calculating proper sign. I'll just take a numerical example after defining this linear magnification. So what is this linear magnification? It is defined as, linear magnification is defined as the ratio of the image to the object height. Okay, linear magnification is defined, it is defined as the ratio of height of image to the height of object. Okay, height of object. See, if suppose the object height, see, we have seen here, if suppose this height of the object is h1 and height of the image is h2, then linear magnification is denoted by small m. Small m is equal to image height is h2 by object height is h1. Okay, as I have considered that the height of the image is h2 and height of the object is h1. See, let me just do one thing. I think I need this figure again. Just a minute. So I need this figure here, this particular figure. Just to establish the relationship between, see, this magnification can be, see, height of the object and height of the image may not be always possible to measure, but then is there any way to find out the magnification, linear magnification, without measuring the height of the object and height of the image? Answer is yes. This magnification, linear magnification, This linear magnification can be expressed in terms of, okay, I'm sorry. Linear magnification can be expressed in terms of object distance and image distance. Let us see how we can do that. Okay. See, image height will take B prime A prime, right? B prime A prime, isn't it? And that is AB. If you take with proper sign, then with proper sign, if we take here, look, okay, maybe let us just go to, okay, here. See, B prime A prime by AB. See what we had written in terms of B prime A prime. See the last equation, equation number 2. This could be written as B prime P by BP, isn't it? So we'll just go with that equation. So B prime A prime, say this, you can write B prime P divided by BP. Okay, we can write that. All right. See here, if we see the height of the image, see this is H1 and this is H2. Actually, if we just go with proper sign, this will be minus H2, because H2 is taken, H2 is measured in the negative direction, isn't it? Okay, so this is negative y direction, and H1 is measured B to A. Okay, B to A is positive, isn't it? Okay, this we can write actually BA. So see, this is magnification. This has got a definition, minus H2 by H1. That is equal to, say, B prime P is, B prime P is minus V, as you know, and BP is again minus U. Object distance. This is image distance. This is object distance. Now see from here, this particular thing, okay, so all right, just a minute. Actually, the real definition is this only. The real definition is this alone: image distance by, like, object distance, ratio of image distance to the object distance. Sorry, object height. Because height is a distance, so that cannot be negative quantity. But see, if we just go with here, like, say, if I just find out H2 by H1, how we are getting H2 by H1 is actually here we are getting negative. So that's why this negative H2 by H1. So here actually we are getting negative sign. Okay. So H2 by H1 is how much? H2 by H1 is V by U with a minus sign here. Okay, just don't get confused. The original definition is this: H2 by H1, that is the image, it is the ratio of image height to the object height. But when we are just going to the real image formed by this concave mirror, there this H2 by H1 is obtained as minus V by U. Okay, in case of, obviously, in case of virtual image, that will be V by U. All right. So what we get finally, the linear magnification as H2 by H1 as minus V by U. So this is this is the magnification. Okay, this is linear magnification. So we have understood the definition of linear magnification. Now in case of convex mirror, what it will be? Actually, in case of convex mirror, this will be positive. Okay, so in case of convex mirror, all the images will be virtual, isn't it? So then it will be always positive. See, for the virtual image, I'm sorry, for the virtual image, for the time being, I'm just erasing this part alone. Let me suppose in case of convex mirror or even in concave mirror also, when the virtual image is formed. So here let me show you. In case of convex mirror, see, all the images will be virtual. Suppose the object is here somewhere. Okay, so image will be behind the mirror. Okay, this is the poly surface. Okay, in case of convex, so this will be enlarged, sorry, this will be diminished image obviously, but that can increase also. So see, in this case, this is the image distance, this is plus v. What is the object distance? In this case, this is the negative sign. Okay, this is negative sign. But what we have magnification minus v by u. Okay, this is the formula with the minus sign inherent. Okay, now if we just put, in case of this, we'll get minus sign over here, then it will be positive v here and minus in the object distance. So this minus will make this as positive. Okay, positive v by u. So magnification for convex mirror is always positive, and in case of concave mirror, there are situations when it will be positive and some cases it will be negative. When the convex mirror will produce a virtual image, that time it will be positive. So the main point is that, so M is positive for virtual image. Okay, M is negative for real image. Okay, real image. So this is one point to discuss. See, a few more things so you can just do with this magnification. I just go to maybe here. See, magnification, linear magnification. With this, you know what we can do. So we have got definition of magnification as minus v by u. Okay, so this magnification can be expressed in terms of, so we know this relationship, right? 1 by v plus 1 by u is equal to 1 by f. I can express this magnification in terms of uf or in terms of fv, like that. Okay, let's see how we can do that. So suppose we want to derive this equation or express this magnification in terms of only object distance and focal length. Okay, we don't have, see, if we don't know the image distance, then how can we proceed and how can we find out the magnification? Obviously, other parameters, if other parameters are known, we can find out the object distance, sorry, image distance. But still, if without doing that also, we can find out the magnification. Okay, I'm trying to say that we are planning to express m in terms of u and f. This is what we are going to do now. So in that case, you know, you have to just multiply u in this equation, u all this side. Okay, so u by v plus 1 u by f, right? So from here u by v is equal to u by f minus 1. Look, this I can write u by v is equal to u minus f divided by f. Now v by u means f by u minus f. So we have got this. See, v by u is equal to f divided by u minus f. Or if you want to make it positive, then f divided by f minus u. So this is in terms of f and u. Similarly, we can get this magnification in terms of v and f. In that case, you know, you have to just multiply v on both sides. Just a minute. So if we multiply v on both sides, so this will be 1, this will be v by u, and this will be v by f. So v by u is equal to v by f minus 1. So v minus f divided by f. So this is the m in terms of v and f. So how we get? For the minus sign, v by u. So this will be v minus f divided by f. Okay. So again, this is f minus v divided by f. So this is the way to find out magnification in terms of v and f. See, we'll just conclude with the spherical mirror by considering few things here. One, defect of spherical mirror, that is spherical aberration. So what is the defect of this? Like, you know, defect of this spherical mirror is if some rays are very far away from the pole. Okay, I mean the marginal rays, you see here, the rays which are very much near to the principal axis are called paraxial rays. So they are actually, after reflection, they are marching at a point here. You can see that they are marching at a point here. But the rays, you see, these marginal rays, they are actually not converging at the focus, even though they are parallel, but they are meeting somewhere near to the pole. Okay, nearer to the pole rather than meeting at the focus. That means, you know, all the rays are not converged by this mirror at the same point. So this inability of a spherical mirror, this inability of a spherical mirror of large aperture actually this aperture spelling is not aperture, aperture. Inability of a spherical mirror of large aperture to bring all or to focus all the rays of wide beam wide beam okay, wide beam falling on the mirror. So it is, so spherical aberration is the inability of a spherical mirror of large aperture to bring all the light, let us write, to bring all the light rays of wide beam falling on the mirror to the focus, or sorry, to focus at a single point. That's why, you know, so you might be thinking, why do we so much bother about this spherical aberration? Okay, so if this spherical aberration is persisting in a mirror, like, or an arrangement of a mirror, you know, this spherical mirrors are being used in, or even in spherical lenses are being used in microscopes. Okay, microscope, or the same fundamental idea is being used in the case of electron microscope as well. So in any microscope, if there is a spherical aberration, then you know what will happen. The marginal rays will meet somewhere near the pole than the principal focus, and since this different uh, reflected rays are meeting at different points, you will see that the rays will meet this curved surfaces, on this curved surfaces. Okay, this curved surfaces, and these curved surfaces are actually called causative curve. And because of this, since all the rays are not meeting at the same point, the reflection, the image will be actually blurred image. Okay, this will produce, so aberration will cause blurred image. Okay, or blurredness of image. Okay, blurred image. And see, if the image is blurred, then you cannot actually see the very fine details or finer details of the image itself, which are required sometime in case of scientific research, etc. Okay, so this is the reason we need to actually uh, get rid of this spherical aberration. So question is how to get rid of get rid of the spherical aberration. Spherical aberration. So how to get rid of the spherical aberration? Get rid of the spherical aberration. Okay. So there are ways to get rid of. First of all, say we can just use some filters, some filters, which can cut off this marginal rays, so that we get just paraxial rays to focus at the single point. Okay, so first point is cut off the marginal rays, marginal rays somehow. So similar type of remedy we can get. See, if we cut off the marginal rays by using some filters or some arrangement, we can actually get rid of this spherical aberration. Okay, so if we use the, see, in case of large aperture itself, see, this is a mirror with smaller aperture, this is a mirror with larger aperture. So in case of larger aperture itself, it happens, actually happens more more notably. Okay, so in case of small aperture mirror or lenses, the spherical aberration is not that significant, but in case of large aperture, we'll have definitely that particular aberration or defect. So for that case, see, if by default we have to use large aperture size of this spherical mirror, then we have to use some apertures to cut off these marginal rays. Otherwise, use mirrors of small aperture, small aperture. Then what else? Instead of using spherical mirror, we can use parabolic mirror. Parabolic mirror. Use parabolic mirror to get rid of the spherical aberration. You look, this is the parabolic mirror. Here, even the marginal rays are also being focused at a particular point. Okay. So in concave parabolic mirror, you can see here there is no aberration, spherical aberration. So instead of using spherical mirror, we can use parabolic mirror. Okay, so these are few remedies, okay, or a few solutions. Okay, now what we'll do, we'll learn about the use of spherical mirror. So uses of spherical mirror, there are two types of mirror, right? Concave and convex. So concave mirror is being used for saving, we'll say first concave mirror. Concave mirrors are used for saving, right? Or in the makeup room. Okay, for makeup. Okay, because it forms a magnified and erect image. Erect image when the face is actually kept closer to the pole. Okay, and doctors, see, in the dentist, like ENT specialist or even dentist, use this mirror over their head. Okay, so this is first thing. Second point, dentist and doctors use this mirror, this type of mirror. Okay, concave mirror overhead. Even in case of surgery also, these mirrors are used. So in the headlights of cars, as a reflectors, okay, used as reflectors in torchlight or searchlight. in headlights of car, searchlight, headlights of cars, searchlight, etc. Okay. What about convex mirror? Convex mirror. See, convex mirror has got its uses in case of the rear view mirror of vehicles. Rear view mirrors of vehicles actually are convex mirror. So why do we use this rear view mirror, convex mirror, as the rear view mirror? Why don't you use the plane mirror? The answer to that is okay. Answer to that is here. In case of plane mirror, the field of view is narrower. Okay, narrow field of view. In case of convex mirror, the field of view is wider. So that is the reason. So at turning point, or maybe we can see actually the whole wide road through this mirror, but through this we can see a part of the road. Okay, that's the point. Okay, so these are few uses of concave and convex mirror. And see, in case of see, parabolic mirrors, the properties of parabolic mirrors are used in this antenna. Okay, this antenna in microwave signal transmission and acceptance. Okay, to collect and bring out all the rays. Oh, sorry, all the waves, microwaves. Okay, and focus at a point, so that like not a single signal is lost. So that's a parabolic mirror is used in, actually parabolic mirror concept is used in this antenna. And parabolic mirrors are used in astronomical telescopes of large aperture for overcoming spherical aberration. Okay, let me just write it. Sorry. Parabolic mirrors. Parabolic mirrors are used astronomical. In astronomical, see, I'll tell you, this will discuss obviously. In astronomical telescope, large aperture is required to collect lot of rays, lot of light. But if we have spherical mirror and use a large aperture spherical mirror, then there will be lot of spherical aberration. So parabolic mirrors are used in astronomical telescope to minimize spherical aberration. Spherical aberration. Okay, so this is the point here. And this antenna, okay, to collect and bring. So this property of this concave concave parabolic mirror, the property of concave parabolic mirror is being used in this antenna. This antennas to collect and focus all the microwave signal into a point, okay, so that no signal or no information is been lost. Okay, all right, we'll stop it here for today with this. Next day, that is tomorrow we'll actually take up various numerical problems related to mirror equation, magnification, etc. So this is the part with spherical mirror is done. Okay, so we'll just take up numerical problems first. Actually, I thought of doing refraction of light, apparent depth, and some few more things with refraction. But now I'm just realizing we should finish numerical problems. So in the next class, we'll do numerical problems. Okay, on mirror equation, magnification, and image formation, etc. Okay, so thank you for your patience. Bye for today.